All right, let's look at the last part of first order kinetics, and this is about half-lives. All right, the definition of a half-life is it's the time that it takes for a reaction for the concentration or the amount of one of the reactants to decrease to 1/2 of its initial value. So if something starts out with 5 grams of reactant, the half-life would be the time for it to decrease to having 2.5 grams. This can also be in concentrations. So if something starts out with a concentration of 0.4 molar, the half-life would be the amount of time it takes to get down to 0.2 molar. Now, what's really important about these is that for first order reactions, and only for first order reactions, the half-life is constant throughout the reaction. So that means that the time that it takes to go from the initial amount to half of that amount is 1 half-life, and then it takes another half-life to go from half to 1/4, and another half-life to go from 1/4 to 1/8, and so on and so forth. All right. So if you're looking at this in terms of concentration, if you've got some reactant A and some time passes, after 1 half-life, concentration will be 1/2 of the initial value. And then during the next half-life, it doesn't reduce by the same amount, but it reduces by the same fraction. So it reduces by 1/2 again. So during that second half-life, it decreases by 1/2 again, and so the concentration would be 1/4 of its initial value, and after a third half-life, it'll go down to 1/8 of its initial value. All right, so for example, if we had a reaction that started with a reactant that had a concentration of 0.12 molar, and the reaction followed first order kinetics, then after 1 half-life, the concentration of that reactant would be 0.06 molar. And after another half-life, it would be 0.030 molar, and so on and so forth. And each of those half-lives is the same amount of time. We can see this in the first order reaction that we did in the first set of videos on the hydration of formaldehyde. So we got the formaldehyde reacting with water to make this methylene glycol. There's a data table over here. This data table is based on the same reaction that I gave you before. I'm not sure if all of these values are exactly the same ones that were in your previous table. I think they are, but they might be a little different. In any case, we've got the concentration plotted on the right-hand side, and we want to see what this constant half-life looks like. So the initial concentration is 0.45 molar. So 1 half-life would be the amount of time it takes to reduce to 1/2 of that, or 0.225 molar. And 0.225 molar is going to be about right here. And so if we, a little higher than that, so if we measure the amount of time required, it brings us down here. That amount of time is 1 half-life. Okay. And since this is a first order reaction, that half-life is constant, so the time required to go to 1/2 its initial value should be the same amount of time required to go to 1/2 its initial value again. Right? So from 0.225 molar, if it decreases to 1/2 that value, that's 0.1125 molar. So we'll call it about 0.11. Okay, so 0.11 is about right here. Bring this over here. Boom. That hits right about there. And the amount of time to decrease from 1/2 of 0.11 is going to be 0.055, something like that. About half of this, right? So let's go here. And if you look at this, what's important is that this distance here, this half-life, this distance here, this half-life, and this distance here, this half-life are all the same length. And again, that's only going to be true for first order reactions. In this particular case, if you look at the graph, you can see where the first one hits here at about 400, the second one hits here at about 800, the third one hits here at about 1200. It looks like I overshot a little bit, but it's about 1200. So for this particular reaction, our half-life, well, let me put a T there. People often use tau for half-life. That's just the Greek letter T. But I think I've been using, I think your book uses T, so we'll use T1/2. So for this particular reaction, the half-life is about 400 seconds. All right, so here's a sample question. Let's say we've got a solution of hydrogen peroxide, and the hydrogen peroxide is decomposing according to first order kinetics, the decomposition reaction. Looks like that. And it follows first order kinetics. The initial concentration is 0.18 molar. Okay. And the half-life is 12 minutes. And we want to know what the concentration is going to be after 36 minutes. Okay. So we can just use our half-life rules, right? So initially, concentration is 0.18 molar, right? After one half-life, 12 minutes later, the concentration will have decreased to 1/2 its original value, which is 0.090 molar. Right? After another half-life, 12 minutes, it's going to decrease to half of that value, which is 0.0045 molar. And after an additional 12 minutes, it'll decrease to half of that, 0.00225 molar. Right? And so this is 12 minutes. After 12 minutes, it'll be this concentration. After 24 minutes, it'll be this concentration. And after 36 minutes, it'll be that concentration. Right? So at 36 minutes, which is 3 half-lives, apologize, getting a little sloppy. Concentration of the hydrogen peroxide will be 0.0. We've got 2 sig figs in there, so we'll round to 2 sig figs. 0.022 molar. Okay. Now there's an important relationship between the half-life and the rate constant. We can see what that is by starting with our equation. The concentration of some reactant at some time t is equal to the initial concentration times e to the minus kt. And we'll see what happens to these values if we plug in let's go ahead and do this. If T is the half-life. Okay. So if T is the half-life, by definition, concentration at the half-life is equal to 1/2 of the initial concentration. Right? So we'll take this value here, which is equal to the concentration of A at time t. We'll substitute it in up there. Right? So this gives us 1/2 of the original concentration is equal to the original concentration e to the minus k t if t is the half-life. Now to get k and t by themselves, let's divide both sides by A0. That gives us this. Okay. And if we divide in this fraction on the left-hand side, we can cancel out the A sub 0. Just boom, boom. And what that gives us is, that gives us 1/2 equals e to the minus k t, when t is the half-life. Okay. All right, I'm going to clear a little bit of space. Bear with me just a minute. I could hit the pause button, but it's nice for us all to get a little chance to catch our breath. All right. All right. So So if 1/2 is equal to e to the minus kt, we can just take the log of both sides. And the log of, well, I'll go ahead and write it out. Log of e minus kt. On the left-hand side, we've got the log of 1/2, and you can just put that in your calculator. And since this is a fraction, the log is negative. The log of 1/2 is negative 0.693. And on the right-hand side, the natural log and the e basically cancel each other out. Right, so we get negative 0.693 equals negative k times the half-life. And since we got a negative on both sides, we can just multiply both sides by -1. Those cancel, and we get 0.693 equals k times the half-life. And this isn't a very convenient way to write this equation. If we take both sides of this and divide by the half-life, then we can get an expression for k. K is 0.693 divided by the half-life. Or we could take both sides and divide by k, in which case we get half-life is 0.693 over k. Right? And notice those two equations look really, really similar. Right? I don't know whether that makes it easier to remember or harder to remember, if it makes it look a little tricky. But just remember the 0.693, and you can also remember that you have to divide by, if you've got the half-life, or if you're trying to calculate the half-life here from the rate constant, right? You've got to divide by the rate constant, because half-life is going to have units of seconds, and the rate constant is going to have units of reciprocal seconds, right? So they've got to be on opposite sides of that fraction. One's in the numerator, one's in the denominator, so that those units come out correctly. All right, let's do it. Let's do an example. All right. So if we go back to the first slide in this little this short lecture, we graphed the concentration of formaldehyde as a function of time, and then we just used the graph to kind of sketch out how long it took to decrease by half, and we determined that the half-life, since we're kind of sketching it out by hand from the graph, right? It's hard to be exactly sure, but it's about 400 seconds. Okay. So if the half-life is 400 seconds, what is the rate constant? So the rate constant is going to be 0.693 divided by half-life, that's 0.963 divided by 400 seconds. Okay. And notice that seconds is in the denominator, so when we calculate this number, we're going to get units of reciprocal seconds. And if you put that in your calculator, you get 0.00173 per second, right? And I think when we did this using the natural log graphs, we got 0.172 or 0.00172. So this half-life was an estimate, so we didn't get exactly the same number, but we got something really close. So this is one of the things that's important here. We have at least two different ways to get the rate constant for a first order reaction. One is if you plot the natural log of a reactant as a function of time, you get a straight line, and the slope is equal to negative k. That's one way to get the rate constant, and that's a good way. That should give you a very precise measurement, right? But another way to do it is if you have concentration of A, not the log, but the concentration, and you have this graph, you can just use that method to see if the half-life is constant, and if the half-life is constant, then you know it's first order, and the half-life is that amount of time to decrease by half. And then once you've got the half-life, you can use that to estimate the value of the rate constant. And of course, also, if you have the rate constant, you can use that to calculate the half-life too. That equation goes in both directions. All right, so kind of a short little video. Important points here. Half-life, by definition, is the time required for a reactant to decrease to 1/2 of its original amount. And what's very important is that for first order reactions, and only for first order reactions, the half-life is constant throughout the reaction. So the time to go from the initial amount to 1/2 is the same as it takes to go from 1/2 to 1/4, which is the same it takes to go from 1/4 to 1/8, and so on and so forth. Okay, and if you can demonstrate that the half-life is constant, then you know that the reaction is first order. All right. And then we did some calculations. Well, we did some algebra, let's put it that way, to show the relationship between the half-life and the rate constant. And we got these two different equations. These are really useful, so you should make sure that you know these equations. and having these ready to use. These are really helpful. All right, that's about it for this video. I look forward to seeing you in the next one.